So if you have the textbook, so you start from chapter 6. Okay, you start from chapter 6 and then followed by chapter 7, 8, and 9. So 6, 7, 8, and 9 is all about convection. Okay, it's all about convection. So in chapter 6, for example, it will explain about the concept of convection. What are the general equation, general terms that you use throughout these 4 chapters. Okay. Okay, so for example, in this chapter, you will learn about the general introduction on the convection, physics of convection, and then because of this convection is heat transfer by fluid medium. Okay, so you need to understand the fluid flow classification. Okay, well, because of conduction is related to the solid, but convection related to the fluid. So under the convection, you need to understand several characteristics of the fluid flow. Okay. Okay, and then this after you understand the fluid flow classification, then you will use your knowledge related to the velocity boundary layer and thermal boundary layer. I think this velocity boundary layer, okay, this velocity boundary layer, you already learned this in the fluid mechanics. Okay, so I can say that this is more related to the recall back what you have learned in the fluid mechanics. But this one is a new. Okay, thermal boundary layer, you only learn this in the heat transfer. Combining this thermal boundary layer and velocity boundary layer, so we can use to convection. Okay. Okay, convection in daily life. Okay. So where we can find the convection problem or phenomenon, I think there is a lot. Okay, the processes are creating the convection effect. Okay, so when you blow your hot food, is basically you are creating convection mechanism. Okay, so the stronger you blow, the faster the food can be cooked. So that is the effect of the, okay. So basically, when you increase the velocity of your air from your mouth, so this means it is increasing the heat transfer. Okay, so this means there is a relation to the characteristic of the fluid. Okay, so this is things that we need to study. Okay, so other application like what, CPU, fan, okay, radiator, steel cooling. So this is all the engineering application that required analysis. Okay, when we compare the convection and conduction, okay, so of course this transfer requires a medium. Okay, conduction require a solid medium, convection require a fluid medium. Okay, but in general, both heat transfer can be occur together, simultaneously occur at the same time. Okay, except if there is no fluid motion, this means conduction is not happen. Okay, but for the convection, you require a Okay, so that's why I think if you still remember the example of the conduction, when we have double layer of a material, okay, let's say you have this first layer, let's say this is a solid, okay, then this is, okay, and within this material A and B, you have air, okay. So basically the heat transfer from left to right, let's say this is the high temperature, this is low temperature. So of course the heat transfer move from the high temperature to the low temperature. So the mechanism inside the air, I mean inside the between this layer, although this is a fluid, but you consider this is a conduction. Although this is a fluid, it is conduction because there is no fluid motion, because this section is closed, okay. So we can say, so because of this is a closed section, so no fluid motion, okay. So no fluid motion. Of course, if you in general, you may say that there is Q convection here, okay, but because of there is no fluid motion, so Q convection we can say is negligible or zero. So that's why the heat transfer from high temperature to the low temperature, even though it is passing solid and also fluid, the heat transfer mechanism only related to the heat transfer by conduction. Okay, so this means conduction in the A, conduction in the B. Okay, so there is no convection if it is no fluid motion. Okay, so under convection you have generally you have two types of convection. Okay, so under convection, so we can say they can divide it into two type convection. One is a forced convection, okay, at which you required some external force or external system to improve or to increase the fluid flow. Another one is a natural movement or natural flow movement. Okay, so basically there is two type of convection. One is a forced convection, second is a natural convection. So if there is no flow, that means the heat transfer only by conduction. Why you didn't consider conduction here? Why we don't consider conduction here? Because of course in general convection when you have a force flow, but because of the value of the conduction, when you compare with a forced convection, the value is more or less I think it's very small compared to the forced convection, even smaller than the natural convection. Okay, so conduction under natural and forced convection is very small. Okay, it's very small. Okay, it's only significant when there is no flow in the in that particular problem. Okay, so back to the type, we have a two type of convection: forced convection and natural convection. Okay, so actually under forced convection, it can be divided into two more category. One is the external force convection. Okay, and another one is a internal force convection. So what the difference is mainly due to the geometry. Maybe the fluid flow is outside of the system or the side of the system. Okay, this is more related to the fluid mechanics consideration. Okay, the geometry. Okay, we will define this later in the specified chapter. Okay. So this is just what I say just now. Okay, even though you are studying heat transfer from one side to another side, okay, and because of there is a fluid here, so you are considering heat by convection. Okay, so in general, Q here should be Q by the convection plus Q by conduction. Okay, but since the conduction value will be smaller, or Q convection will be much higher than Q conduction, you can say that heat transfer by the fluid is mainly due to the Q convection. If you want to calculate, still can, but the value is not very significant. Okay. Okay. So how to calculate the heat transfer by convection? So this is the heat transfer rate by convection. I think you're familiar with this equation. And in fact, we already used this equation. Okay, the first equation is in terms of heat flux. Okay, this is called heat flux, heat per unit area, and this is a heat rate. Okay, so what the different? One is with area, one is without area. So the value or the symbol is represent H convection, heat transfer coefficient, surface area that that you want to study from where the heat is coming from or going to, and then Ts is surface temperature, and T surrounding is far field temperature. Also, I can say it's a surrounding temperature. Temperature, or sometimes we call it a fluid temperature. Okay. So you already learned this equation. Then why this heat transfer mode for chapter to explain the convection? Okay. So why this convection require 4 more chapter? Okay. Because we need to define the convection due to the several parameters. Okay, when you look back to this equation, okay, well, area is the area, temperature is the temperature. You just measure the temperature, whether you are using a digital device, digital thermometer, or you can use analog thermometer. The challenging part is how to define H. Okay, how to define H. What is H? H is convection heat transfer coefficient. Okay, because if you look in the first chapter, they give you some range. Heat transfer coefficient is within this range if you are using air. But if you are using water, the heat transfer coefficient will be within this range and this range. So the value is not exact. It's not accurate. Not say accurate, it's not exact. It's not in the one final value. Okay, so that's why under convection, we need to consider several parameters. So what control convection? There is three factors that control convection. One is a fluid properties, okay, whether the fluid is air or liquid, because this will be can be defined by the density, okay. Geometry, whether you are using geometry can be in the different shape or in the different um, surface finish, okay. Probably if you are using rectangular ducting with circular ducting, okay, so the convection will be a difference, okay. And some more, if the surface, because there is a calculation of area, if the surface you are using with different surface roughness, one is a smooth, one is a rough, so this will create different value of convection coefficient. For the third one, okay, type of flow, okay, you learn in the fluid mechanics, the type of flow can be divided into three categories. You still remember what it is? Laminar, turbulent, as well as the transition. So this will be parameter that control the convection. Okay. So for example, fluid properties. Okay, like I say just now, density. So fluid properties that may affect the H value. Your aim is now, you have to remember your calculation is just this simple, QHA delta T. You know this, but the challenging is how to find H. So in order to find H, you need to know the density, you need to know the thermal conductivity, you need to know the viscosity, fluid velocity, and specific heat. Okay, so you can see how much now the condition will be a bit more complex compared to the conduction. In the conduction, you just need a K value. That's it. Once you find K, you can calculate the heat transfer by conduction. But for the convection, in order to find H, what is H? H is heat transfer convection coefficient. So you need to have, or you need to know the properties of the fluid. Okay. So this is another information related to the parameter that control the convection. Okay. So like I say, this is effect at which you need to know whether the fluid flow is what type of the fluid flow. Okay, so imagine this is your surface, this plate. Okay, so this plate, this is what you want to study, or in fact this is the temperature is a bit higher, T high, and this is a T low. So of course, because of you have a different temperature, so there will be action heat transfer throughout the plate. Okay, Q convection. So you want to calculate the Q convection. HA delta T. HA TH minus TL. So now you can find the area, you can find the delta T, but the challenging part is how to find H. And you know that if this is a plate, if the fluid flow is coming in this direction, you may have a different fluid profile, fluid flow profile. Okay, so meaning this is related to the velocity fluid layer. Okay, why this is important? Because from this velocity layer, you may find here will be lamina, and probably here you got transition, and later part you may get turbulence. So each of these fluid profile will give you different H value. Okay, so for this reason we need to know how much or how big the plate that we need to study. Okay, whether the lamina is more significant or more dominant, or whether transition is dominant or turbulent is more dominant. So depending on the condition. So like this topic is talking about sleep condition. Okay, so this sleep condition is very important in order to define the velocity profile. Okay, so from the sleep condition, you can have this boundary layer. So from the boundary layer, you can get the lamina, transition, and turbulent. Okay. What fluid properties govern the formation of the boundary layer? So basically, it's a viscosity. Okay. So the viscosity properties is important for you to define whether it is a lamina, transition, or turbulent. Okay, so you know the viscosity is very important. So to relate this kind of properties, okay, so you need one dimensionless number called Nusselt number. Okay. So what is a Nusselt number? Okay. Actually, if you still remember in the previous topic, we learned about Bayard number. Okay. So what is the Bayard number? If you still remember, what is the Bayard number? Bayard number is a Q convection divided by Q conduction. Okay. So seems that it is a same like a Nusselt number. Okay. So what is the difference between Bayard number and Nusselt number? Okay. Both number is calculating the resistance due to the convection over the resistance to the conduction. Okay, resistance due to the convection divided by resistance due to the conduction. But it's same. Okay, so what is the difference? The difference is the Nusselt number related to the fluid medium. Okay, but for the Bayard number related to the solid medium. Okay, and Nusselt number used for the convection analysis. And for the Bayard number applicable for the conduction analysis. Okay, so don't confuse between the Bayard number and Nusselt number, even though the value or the equation is the same. Okay, so if you look Bayard number, it's also H, L, or K. Okay, Nusselt number same, is a H, L over K, but this is for the fluid. Okay, for the fluid layer. Okay. Okay, next one. So like I say, we need to understand the fluid flow characteristic or fluid flow classification. Okay, so these are the example of the properties or the parameter that you need to understand, okay, in order to okay. So first, you know the viscous, okay, which is the opposite viscous is inviscid, okay, and you need to know whether the fluid flow is an internal or internal flow or external flow, compressible or incompressible, okay, compressible or incompressible. What meaning by compressible and incompressible? Uh, Before that, viscous and inviscid. Do you know what the difference? Viscous means the fluid have some viscosity value. This means there is some force due to the viscous motion. Inviscid means the viscosity value is very, very small, okay, like air, okay. Air is considered fluid and there is some viscosity, but the viscosity is very, very small, and because of this we say that this is an inviscid flow. This means the effect of the viscosity can be negligible, okay. Internal, external, you know, internal flow, external flow is depending on the geometry. Compressible and incompressible, whether you can compress the flow, the fluid. Okay, the example of compressible is air. Incompressible is a liquid like water. Okay, so anything that can be compressed, okay, most of gases can be compressed and it is considered compressible flow. But like a liquid, it is incompressible. You cannot compress water. Okay, then another type is lamina and turbulence. Okay, lamina, you know, lamina is the type of the flow which is less resistant, or the fluctuation of the velocity in the lamina is very smooth, very uniform, but in the turbulence, the fluctuation of the fluid flow in terms of the velocity will be high and very random. Okay, this is the explanation. Okay, viscous flow and inviscid flow. External versus internal. Okay, so it's related to the geometry, whether you are the flow is going outside or inside of the system. Okay, compressible and incompressible. Okay, density. Okay, the easiest one is when the density is a constant. Okay, uh, okay, if density is not constant and changing with the flow, okay, like high speed gas, so it considered compressible. Okay, laminar, turbulent, okay, just the different in terms of what is the way to characterize the laminar or turbulent flow? I think you use a Reynolds number. Okay, so Reynolds number used to characterize the flow type, laminar or turbulence. Force flow and natural flow. This is another type of flow. Okay, force flow meaning that there is external system or external means, okay, such as pump or fan, used to force the fluid to flow. Okay, also when you blow the air, uh, basically you are introducing a force flow, even it's not very strong, but still it is a lot higher compared to the natural flow. And what is the natural flow? Natural flow is the flow that still move, but due to the buoyancy effect. What is the buoyancy effect? So buoyancy effect is basically due to the difference in density, okay, at which manifests itself as the rise of warmer fluid and the fall of the cooler fluid, okay. Buoyancy effect happen due to the density, okay. So like you have air, let's say this is the air. So air will move downward if it is cooler, and it will move upward if it is hot. So why this movement is occur? Because of the density. You may say that, oh, density A is 1. So of course it is 1, but if you want to find the difference, so the value is not same. It's not actually 1. Okay. In fact, this probably 1.1 or 1.0 something, but this probably 0.9 or 0.95, which is a bit lower than the cooler air. The concept of air conditioning. So that's why when you are having the air conditioning, so the cooler air will move downward, and the heat that you are creating by your bodies producing hot air, and it will move upward. Okay, so this actually is a buoyancy effect. Okay, because of the density movement, because of the density value. Steady versus unsteady, I think you know this. This is just a matter of how change the properties as a function of time. Okay, the term steady implies no change at a point with time. Okay, so in most cases, our analysis will be in steady state. Okay, okay, boundary layers. Okay, before we go to the application of equation that used to calculate H value, you need to know the velocity boundary layer and thermal boundary layer. Okay, or you need to understand the velocity boundary layer and the thermal boundary layer before you apply the equation in the particular condition. Okay, so what is the velocity boundary layer? So in the velocity boundary layer, you required some velocity values, okay, before it's starting or before it's coming to the edge. So basically, it is a constant from top to down, or constant throughout the profile. But once it's going pass through the plate, okay, let's say this is the plate, okay, let's say this is the plate, so the fluid velocity will be vary, okay, and this variation is related to the friction resistance, okay. So the difference between the maximum, sorry, not maximum, the maximum value of the velocity compared to the velocity at which will be nearly zero is considered the boundary layer thickness. Okay, so you may need to know how to calculate the boundary layer thickness. Okay, if you do a friction resistance in this particle. Okay, so um, develop the flow profile on a plate. Okay, let's say this is the plate. Let's say this is the plate that you want to study. Okay, so if the plate is long enough, So you may find at the first part of the plate, okay, after the flow is passing through, so you may find lamina boundary layer, okay, and then followed by the transition, and further, if it is long enough, then you have the boundary layer. Okay, so if these are the conditions that you may find in your problems, you need to know which layer is a dominant, whether is lamina is dominant or transition. Transition is a bit difficult because transition is very small compared to lamina and turbulent. Okay, probably lamina and turbulent is a close. Okay, if you use a certain length of the plate. Okay, if you use a plate that very long enough, probably turbulent will be dominant compared to the lamina in transition. So this is how you need to understand the how to define the flow type, okay, before you calculate the H value, the convection coefficient. Okay, shear stress. Okay, this is related to the velocity boundary layer. Okay, once you calculate the friction force, okay, from the velocity boundary layer, you can estimate the shear stress related to this velocity profile. Okay. Okay. Skip this viscosity. This is just a viscosity value. Friction coefficient. Okay. Friction coefficient. So from the velocity profile, okay, normally what we can do is we can find the friction coefficient. Okay. So from the friction coefficient, okay, you can find later the shear stress. Okay, once you calculate the shear stress, you can find the friction force. Okay, but this one is mainly the related to the force that occur due to the velocity movement. Still, we not go into the heat transfer yet. Okay, but for some reason, the friction force, okay, can be related to the heat transfer coefficient. Okay, actually, we don't really interested in the friction force because this is the heat transfer analysis. Uh, However, because of this friction force, have some factor related to the heat transfer coefficient and power requirement. For this reason, we need to understand how the friction coefficient can be used to define the heat transfer coefficient. Okay, so how to relate this? Okay, first we look into the thermal boundary layer. Okay, so what is the difference between the thermal boundary layer and the velocity boundary layer? So if the velocity boundary layer related to the difference in the velocity, thermal boundary layer is a layer related to the difference in temperature. Okay, so different in temperature. So imagine the temperature before going to this plate. So you may find the temperature from up, from downside, close to the plate, up to the later layer, upper layer. So it will be in the same value, surrounding temperature, far field temperature. But when you are moving to the close to the plate or on the plate, so you have this temperature profile. Okay, so if the temperature is smaller than the surface, so you may have this temperature difference. Okay, so this temperature difference can create a thermal boundary layer, And from this, you need to understand how to relate the thermal boundary layer, velocity boundary layer. Okay, so one way to define the thermal boundary layer is using Prandtl number. Okay, this is another dimensionless number. Okay, so because if you look back to this thermal boundary layer, it's a bit difficult. It's not related to the lamina or transition, lamina or turbulent. Okay, if the fluid boundary layer related to the, if the velocity boundary layer related to the transition of lamina to turbulent, and you can define by the Reynolds number. For thermal boundary layer, you require a Prandtl number. I think this is the second dimensionless number. Okay, the first one is a Nusselt number. Okay, so Nusselt number is a resistant, the heat resistance of conduction to the convection of the fluid flow. But the Prandtl number is another dimensionless number. Okay, it's a dimensionless number used to characterize the relative thickness of the velocity thermal boundary layer and thermal boundary layer. Is basically, if I can calculate this, this is delta V divided by delta E. Okay, thermal boundary layer due to the velocity divided by thermal boundary layer divided by boundary layer due to the thermal boundary layer due to the velocity. Okay, but to calculate this is a bit difficult. Okay, it's a bit complex. You need to have a lot of equation to integrate. So one way to calculate the Prandtl number is using the diffusivity of the momentum divided by diffusivity of the heat. It's basically the properties of the fluid in diffusivity of the heat. And this can be translated into the more simplified properties, which is dynamic viscosity. So this is kinematic viscosity divided by thermal diffusivity. Okay, and if you don't use this one, you also can translate into more simplified properties like dynamic viscosity times the specific heat. Oh, there is no Cp here. So Cp is a specific heat. Okay, divided by K, which is thermal conductivity. Okay, so that's why in the early part, we need to know the Cp, we need to know the K value, we need to know the viscosity. So all this will be translated into a new dimensionless number called Prandtl number, at which this Prandtl number used to define thermal boundary layer as well as the velocity boundary layer. Okay. So what is the Prandtl number actually? Let's say you calculate Prandtl number. What is a Prandtl number meaning? Okay. So based on the definition, Prandtl number is how good the velocity diffused compared to the how good the heat is diffused. Diffuse mean what? Absorb, okay, to that particular fluid. Okay. For example, for liquid metal, heat diffuse quickly. Okay. So Prandtl number is very, very large, larger than 1. Okay. Is it true or false? It's a false. Okay. For the, this is related to the how you compare the velocity boundary layer and the thermal boundary layer. Okay, in terms of the properties. Where is the table? I want to show you the tables of the Prandtl number. This is just okay. go to this one. Okay, we don't consider metals because metal is a solid, but we consider liquid metals, and then we compare to the gas, air, light, organic fluids, and oils. Okay, so if you look here, what we can see is the viscosity will be, I can see the viscosity here is increase. As you're going down, viscosity is increase. Okay, but when you're going down, the heat transfer is reduced. Heat transfer will better when you are going up because it is a liquid metal. What is the good example of liquid metals? Mercury, your thermometer liquid. Okay, so liquid metal will have a smaller Prandtl number. Okay, gas will be nearly 0.7 to 1. Water is a bit larger, but oils, engine oil, glycerin, okay, very thick, very thick. This is very high viscosity fluid will have a larger Prandtl number. Okay, so meaning it's hard. The larger the viscosity, is not very good in terms of heat transfer. Okay, so this is related to the how we can define the Prandtl number in order to calculate the heat transfer convection coefficient. Okay, there is more to 2 or 3 slides. Okay, time is not nearly finished. Any question so far? I should give you some example, but I think the example I will give you in the tomorrow class related to the how to use this kind of dimensionless number in order to define the convection coefficient. Any question? Okay, if not, I think we'll stop here. Okay, because there is several slides related to the several dimensionless number for the convection. Just to remind you that under this convection we will use I think quite a number of dimensionless number. Okay, for example, we use a Nusselt number, we use a Prandtl number, we use a Reynolds number. Okay, before we calculate the H value. So we need to know Nusselt number, Prandtl number, and as well as the Reynolds number. Okay, before you want to calculate the heat transfer convection coefficient. Okay, no question. Actually, all what I have explained just now is already in the textbook, but in the lengthy explanation. You can read the textbook if you want. Okay, but I hope you can read it so that if you have any question related to this fundamental terms, the terminology, the general properties, okay, parameter related to the convection, you can ask me during the class. Okay. So if not, I think that's all for today. We will come again in the next tomorrow class to complete this the topic of convection. Okay, so with that, thank you very much.